Problem 56 is asking us to show that a planet's density can be equated to 3 pi over gt squared if a satellite orbits it close enough to its surface. So what this problem assumes is that if we have a planet and a satellite is in orbit around it like so, and the orbit of the satellite is close enough to the planet, we can determine the density of that planet. If the satellite is in a circular orbit around the planet, then its orbital velocity can be determined using the equation 2 pi r over t, where r is the distance the satellite is from the planet and t is the satellite's orbital period. Now, this formula alone won't help us find the planet's density. We're going to need something for velocity that involves mass. That's where this formula comes into play. Here, velocity is equated to the square root of the gravitational constant g times m over r. M is the value of the planet's mass, and r, like I said earlier, is the distance the satellite is away from the planet. So, since both these formulas are determining orbital velocity, let's set them equal to each other. The square root of g times m over r is equal to 2 pi r over t. Mass is going to be important in finding our planet's density, so let's square both sides to get mass out from under that square root. Now we'll have g times m over r on the left-hand side of the equation, and 4 times pi squared times r squared divided by t squared on the right-hand side. The gravitational constant isn't necessary to have in finding our density, so let's divide both sides by g. That'll give us m over r is equal to 4 pi squared times r squared divided by g times t squared. Let's also put r on the left-hand side with m. So, dividing both sides by r squared, we'll now have m over r cubed is equal to 4 pi squared divided by g times t squared. Now, why did I put r on the same side as m in that part of the problem? It's because density is equal to mass divided by volume. And assuming our planet is perfectly spherical, its volume will be equal to 4 over 3 pi r cubed. We can substitute that equation for volume into the denominator of our formula for density here to get m over 4/3 pi r cubed, which we can then rewrite as 3 times m over 4 pi r cubed. Now, notice that we have an m over r cubed in our equated expressions for orbital velocity up here, and we also have an m over r cubed in our expression for density down here. Since the expression above showed us that m over r cubed was equal to 4 pi squared over g times t squared, let's go ahead and substitute that in for m over r cubed in our density expression. Now, we'll have 3 over 4 pi times 4 pi squared over gt squared. Canceling out the 4 and the pi in the denominator, we get a value of 3 pi over gt squared, which was the expression we were asked to prove in the first place. So now that we have our density expression proven, let's put it to the test by trying to calculate Earth's density, given that there's a satellite in a near-Earth orbit around it, circling it every 85 minutes. The first thing we need to do is convert 85 minutes into seconds so we can solve our problem more easily. 85 minutes times 60 seconds over 1 minute. If we do our cancellations and multiply through, we get a value of 5,100 seconds for our period. Now, let's try and solve for Earth's density. Rho sub e will be equal to 3 times pi divided by 6.67 times 10 to the minus 11 newtons times meters squared over kilograms squared, the gravitational constant, times 5,100 seconds squared. When we do the math and calculate our way through this equation, we get a value of 5,433 kilograms per cubic meter for Earth's density, which is only about 1.5% off of the actual value for Earth's density of 5,515 kilograms per cubic meter.